Uh, Good evening, everyone, and good morning to ma'am. My name is Rahul Marik. I'm the of IEEE SPS student branch IIT Kharagpur, and I request Supara, Secretary of IEEE SPS, to introduce our next.
Hello attendees, we welcome you all to this IEEE webinar, which is organized by IEEE Signal Processing Society student branch of IIT Kharagpur. Today's speaker is Professor Zhao, who is currently a Joseph C. Ford Professor of Engineering in the Department of Electrical and Computer Engineering at Cornell University of Ithaca, New York. In 2001, she received her PhD degree from Cornell. Later, she joined University of California, Davis as a professor in EC department. After that, she joined back Cornell University in 2015. Her research interests include sequential decision theory, stochastic optimization, statistical inference and machine learning, and algorithm theory with application in infrastructure, communications, and social economic networks. Professor Zhou is a fellow of IEEE, a Marie Skłodowska-Curie Fellow of European Union Research and Innovation Program. During her one-year sabbatical leave, she won the title of Jubilee Chair Professor at Chalmers University. She also received 2010's IEEE Signal Processing Magazine Best Paper Award and Young Author Best Paper Award from IEEE Signal Processing Society in the year of 2000. Today, she will be speaking on the title of Random Walk on a Tree for Stochastic Optimization and Learning. Before starting the presentation, I would like to mention that we will discuss the question and answer after the session completes. So attendees are requested to leave their questions in the chat section below. And now I request Professor Zhou to start her talk, please.
Okay, thank you. Thank you everyone for joining. Many thanks to Rahul for inviting me. So let me try to speak here. So today we will actually talk about a class of problems. The general theme of the problem is how to efficiently search for a few rare events or extremely useful information in a very large search space. The search space can be discrete, it could also be continuum. And I will present a solution framework that works well for this class of problems. This is a joint work with my former student, Sudeep Salgia, which actually graduated from IIT. Is a great student. We all love students from India. They have very solid foundation. They always excel in our PhD program. And also former student Sattar Vakili, who just recently graduated. So I will start the talk by giving a few motivating applications. So what kind of applications where we see this type of rare event of extreme information detection of learning problems. We'll first consider a few problems where the search space is discrete, countable or finite. The first example is surveillance testing, which is very much related to the situation we're currently in. What we are facing here is we have a large population, and we want to identify a small fraction of people in this large population that are infected. For example, the current pandemic situation. And the goal here is to identify the infected individuals with minimum number of tests when we are facing a large population. Another example is internet traffic engineering. So in internet measurements have shown that internet traffic flows are either the so-called elephants or mice. What that means is the traffic flows in terms of their volume of the number of packets per unit time is either very large or usually is small. So a small number of elephants, in this case called heavy hitters, actually make up most of the total traffic volume. What I plot here in the figure on the left hand, this is a router. So there will be a large number of flows, high-speed internet flows that comes into the router and needs to be routed to different, essentially, destinations. And this is the illustration of one flow that is elephant. And the heavy hitters could be the so-called denial of service attacks that try to bring down a particular server. So it's important to detect such heavy hitters. But the challenge here is there's only a small number of high-speed counters at a router. So the router cannot really keep a packet count of every flow at all the time. So then in this case, with a limited number of counters, we have to decide which flows to monitor at each given time so that we can detect the heavy hitters quickly and reliably. Again, we can see the search space essentially would be all the traffic flows that flows through this particular counter, and again, the search space is discrete. The rare events here would be those small number of heavy hitters, high volume traffic flows. Similar example is in the application of cognitive radio, or the also called optimality spectrum access. What the secondary user facing here is trying to find the unused channels at any given time, that's so-called white space. So in this case, the rare events represent opportunities. So it may not be an anomaly that we need to guard against. Rare events could also be very good opportunities we want to catch quickly before the opportunity disappears. So these are a couple of examples where the search space is discrete. Next, I will give some actually more general problems where the search space is actually continuum. So the first this is actually a general problem. It's called stochastic root funding. The problem here is we have a system, a nonlinear system, but memoryless. It's put it in a black box in the sense that we don't really know the response of the system. So we'll call it the G of X. If X is the input to the system, G of X would be the response of the system to the input value of X. And this is a nonlinear function. The response is nonlinear and unknown to us. Okay? What we want is to find an input value to this black box system and to drive the system to a desired outcome. So we want the system to have a desired outcome. And without loss of generality, we can make the desired outcome to be 0. Because any fixed value, say 97, you can always subtract that known desired response from this generic unknown response. Okay. So we can just set the desired response to be 0. Then what that means is, if we look at this response function, we are trying to find the root of this nonlinear function, or the 0 crossing of this nonlinear function, plotted as x star. If we input x star, the response will be 0, the desired response. But because we do not know this function g of x, it's like solving a nonlinear function. This could be high dimension, x could be high dimension. So in this case, if we do not know the response gx, we can only try different values of x. At each time t, we try a particular value. We use this value to excite the system, and we will observe a noisy response. Bias means on the mean, it equals to the true response at value x. So if we excite with value xt, we will see only the response at the value xt. And based on that, we adjust our value to input to the system at the next time t+1. And the goal is our input value xt would converge to the optimal input x star that will give us the desired response. So this is a very general problem referred to as stochastic root finding. The root here is x star. Stochastic refers to the fact that our observation is noisy. That's essentially a stochastic process we are observing here. So next, I will show a specific application where we are essentially solving the stochastic root finding problem. And this is a traffic planning problem in maybe urban or a city area. What we want here is to decide on which road we want to set a toll booth to essentially ask drivers to pay for using the road, and what would be the price we should set for each toll booth. And we want to choose the location of the toll booth and also the price, the toll price, so that the traffic over this area would be distributed in a desired fashion. We want to essentially drive this system to a desired traffic distribution. Okay, so this would be the desired traffic distribution would be the desired response we want. And this system is unknown in the sense that we do not know how individual drivers would respond to the toll price. Okay? So it's usually probabilistic, and we do not know what's the probabilistic model on the individual driver's response to price. And what we can do is we can do run simulations, which can be costly and subject to error, to noise, and may take time. So we can try in simulation particular locations of toll booths and the prices and see how the traffic distribution look like and then adjust. So this is an application for the stochastic root finding. The next problem, again, the search space is continuum. So I want to mention, maybe go back a little bit. Here, what we are searching x star, this could be a real valued vector in a high dimensional Euclidean space. So in the sense that the search space is actually can be a high dimensional Euclidean space. It's not conical, it's a continuum search space. And x star is like an extremely useful single point in the Euclidean space. Clearly, it's not possible for us to try every point in the continuum space, and we can only hope to get close to x star as quick as possible. Another general problem is so-called the stochastic optimization, which also called black box optimization. This again is a search problem that involves a continuum space. So what we have here is an objective function, I'll call it f of x, that is again unknown to us. So this objective function is in a black box again, unknown to us, and is also a stochastic function in the sense that it is given as the expectation of some random loss function. So this is our random loss function, capital F, it's a random function. X here is our decision variable, is the values of the, we try to decide what would be the optimal value. And C, the red Greek letter here, is all the random factors in the system. It's essentially a random vector here indicating noise or other random effects in the system. that is certainly out of control to the decision maker. And capital F is the loss function if we choose our decision variable x and at a particular realization of the random effects, and we take expectation over all the random effects in the system, and that's the expected loss f of x that we want to minimize. So we try to find x star and minimize the expected loss. The trouble here is, in general, we may not know the distribution of all the random effects in a very complex system, so we cannot really analytically evaluate the expected value of the random loss, so this objective function is unknown to us. So how do we optimize choosing the optimal action x star without knowing the objective function? So in this case, the optimization problem can be viewed as a learning process, similar to stochastic root finding. We essentially try to converge to the optimal value x star over time. At time t, we try a particular value of decision variable xt, and based on that, it applies to this system. We would observe a random loss, capital F, which is a realization determined by realization of the random effects of the system. For example, the specific noise value at that particular time of the system. And then based on the loss we see, that gives us some idea of how good our current choice of xt is. And then we adjust our xt at the next time. And again, we hope to find that optimal x star, or approach that optimal value x star as quickly as possible. And again, the x star could be in a high dimensional Euclidean space. And I'll give an example on where a stochastic optimization problem may arise. This is, again, a typical machine learning problem, the so-called concept learning from examples. So essentially, it's a classification problem. I'm just using a very simple example where we try to classify images of dogs and cats. So essentially, when we see an image, we try to label it as either cat or dog. And the feature for doing the labeling, we're just using the facial width to height ratio. As we can see, the dogs usually have a longer face, so the width to height ratio would be smaller. The height is a bigger, width is smaller. Cat has a more round face, so the height ratio would it does not fully determine. It cannot be perfectly determine whether it's a cat or dog. So what we have is this probability that this figure, this image is indeed a cat, given a particular value of facial width to height ratio. So this is given the feature value, what's the probability is actually a cat. So we do not, the probability in general will not just be 0 or 1, which will be a deterministic relation between feature and label. So as I illustrated here, this probability could be some general function, but as we said, in general, if the width to height ratio is bigger, then the probability is a cat would be bigger. May not be monotone, but this is the case we have here. If we do know this probabilistic model, what's the probability the image is a cat given a particular feature value, then we would be able to find the classifier, the optimal classifier that minimize the classification error, would be doing a threshold on the facial width to height ratio, and the optimal threshold will be x star. That's exactly when the probability is half. So that's where you can say cat or dog with equal, will be either label would be equally likely to be correct or wrong. And if the ratio is smaller than x star, we should say stock, that will minimize the probability of error. If it's greater than x star, we should say cat, that will minimize the probability of error. So this would be the optimal classifier given by a threshold on the width to height ratio. But we do not know this probabilistic distribution, so how do we find the optimal classifier? And then we can view this problem as the stochastic optimization. So essentially, as we think here, the random loss, this capital F, would be the loss or classification error. You can attach a particular loss function to the classification errors. For a particular classifier, x here is our decision variable. That's the classifier we are trying to use. And the random vector, you can see here, would be a specific image or realization of the image we see that's given by the feature value and its corresponding label. Okay? So if we apply this classifier x on this specific realization of the image, we would have a specific realization of loss, capital F. And we want to find a classifier x that minimize this loss with respect to the entire distribution of images that we may need to label. And we can learn this optimal classifier x by trying different classifiers and trying different classifiers on different examples. That will be some labeled images that tells us, okay, this is a cat, this is a dog, and we try to learn from those labeled examples, try to figure out what would be the overall optimal classifier for the whole potential distribution of feature label dependency. And our goal is try to find a classifier over time that converges to the optimal classifier x star. And there are different formulations of stochastic optimization in terms of what are the feedbacks or what are the information we're using for adjusting our classifier or our decision variable xt here. One is the so-called zeros order stochastic optimization. In this case, we're directly using the loss we see, the random loss we see when we choose decision variable value equal to xt and apply it on a particular realization of the random components in the system, and we adjust that. And the other one is the so-called first order observation. So in this case, when we use the decision variable xt, this is a loss we incur that will measure our performance. But in terms of learning, we actually use the gradient of the loss function. The gradient is also a noisy estimate of the gradient. So g of x, lowercase g of x, is a gradient of the objective function f of x. And what we see is a noisy estimate of the gradient only at where our current decision variable x of t. And all we require is this gradient estimate is unbiased. That means the mean of this random estimate equals to the true gradient. And in terms of performance measure, so if we have a learning algorithms, how do we evaluate how good it is, or the so-called learning efficiency? Traditionally, the algorithm is measured by the convergence of the choosing decision variable xt, whether xt will converge to x star, or the function value, essentially our loss, as time goes, eventually converge to the minimum loss of f of x star. The other class of problem actually view this problem as the online learning problem, where the performance is measured by the so-called cumulative regret. That means from the first moment, t equal to 1, our choice of x1 would incur loss that is essentially meaningful, that we consequential. We would have to consider what is the loss at every given time in addition to the minimum loss. This would be, in the parentheses here, this would be the additional loss in excess to the optimal point. Okay? And we add up all the excessive loss over a learning horizon of capital T, this would be the so-called regret. And this is, of course, xt, our decision variable at each time t, is determined by our learning policy, our learning algorithms. So this expectation is over the learning algorithms we are using. Different learning algorithms will lead to different choices of xt and essentially resulting a different stochastic process. So this is so-called cumulative regret. Cumulative regret is actually a finer performance measure than merely the convergence property of the algorithms. So what it essentially says is, if this cumulative regret grows sublinearly with a horizon length t, then we know our loss is converging to the minimum loss of our fx star. But it's not true vice versa. So even if we know algorithms that give us a loss that converge to fx star, that does not necessarily mean the regret actually is sublinear. So what we will see, we want the regret to grow with time t as slowly as possible. So if we have a regret that grows at the order of log t, that's much better than having a regret that grows at the square root of t, which means the convergence would be much slower with respect to the learning horizon. So we can also show a connection between these two continuum search problems. One is stochastic root finding, we said at the first, and then the stochastic optimization. So we can see for stochastic optimization, if the objective function fx is convex, okay, so it's a convex function. So in this case, the minimizer, if you want to minimize fx, then the minimizer x star essentially is where the gradient is 0. That means we are trying to find the root of the gradient of this function, g of x. So this is just like stochastic root finding. So we have, you can treat this gradient function as an unknown response of a nonlinear system, and we try to find the root of the response of this system. So the first order stochastic convex optimization is exactly just stochastic root finding. So these two problems are indeed equivalent if we are doing first order stochastic convex optimization. And these are just some of the problems. Some are really general problems like stochastic root finding and stochastic optimization, but we can all put them in one class. We can phrase it as searching for the rare. And we can see the challenges for this class of problems. First, we're facing a massive search space. The search space could be discrete, as in the surveillance testing problems. It could be continuum and high dimensional, like in stochastic root finding and stochastic optimization. And we cannot check or monitor every possible points in the search space and try to evaluate them and find the optimal one. That just cannot be done because samples are costly and our observations are noisy. There's high uncertainty in what we observe. And also the underlying probabilistic models are also unknown. So it's really a learning problem we are facing here. And the essentially high-level question we want to ask is, facing this class of problems, how do we search efficiently when we are facing a massive search space and our observations are noisy and the models are unknown? And we can essentially, in terms of our objective, we can pose the problem as an inference problem, which means we want to minimize the number of samples we need to find the rare events with a required accuracy. Or we can phrase it as an online learning problem, which is minimizing the cumulative regret. That means instead of only worrying about the end point, that's the inference problem. Inference problem, you don't care about what you are doing in the inference process. You only worry about the decision you make at the end of the process. And this is, you can just say, this is my estimate of X star. The It doesn't matter before you reach your decision what are the different acts you are trying. But for online learning problem, the regret actually captures all the additional loss you see during the entire learning process. Your first choice of X is already, the performance is already factored into the regret. So I will essentially focus on the stochastic convex optimization problem as an example, and you take the online learning framework, which our objective, we try to minimize the cumulative regret. And this is a case where the search space would be a continuum. It's a high-dimensional Euclidean space. And we will present the solution framework for this problem first, and then we will go back to the few examples with discrete search space and see how we can apply the solution framework to those cases. So stochastic optimization actually is a classic problem. It's a very old problem, first studied by Robbins-Monro in 1951. They are considering, they actually are considering the stochastic root finding problem. You try to find the root of a nonlinear system that is unknown to us. This, as we already said, is the same as optimizing or minimizing a convex, unknown convex stochastic function. And the solution they propose is the widely used stochastic gradient descent, SGD, that is so currently very widely used in all the neural network training or many machine learning algorithms. So the algorithm is very simple. The idea is very clean. So at the time t+1, what would be the decision variable we use is just based on our previous point, xt, our previous decision at time t, we move from xt in the opposite direction of the gradient. So g of xt is the random gradient we observed at xt. So we move in the opposite direction of that so that we move toward the minimum. And then eta t here is a step size that essentially is determining how big a step we're taking toward the opposite direction of the gradient. Okay? And we can see this step size, eta t, needs to diminish to 0 as time goes if we want to converge to the optimal point x star. Because if eta t is not diminishing, if it's a positive value, and because this noise in the random gradient will never diminish, there's always positive noise variance there. So if eta t doesn't diminish, then we will never converge to x star. Even if xt is already at x star, then we will be moving, oscillating around x star due to the noise effect in our observation of the gradient. So now the question would be, okay, we know the step size eta t needs to diminish to 0, but how fast? How fast should it diminish to 0? And to do that, we need to take a closer look at our random gradient. Okay, this is our random gradient. We can write the random gradient observation as the true gradient, g of x plus noise, because the noise will be 0 mean because our gradient, the mean value of the random gradient is just a gradient function, lower g of x. Okay? So we can see the step size actually is applied on both of the gradient, which is our signal, because we try to find what is the value of x at which the gradient is 0. So we are moving in the gradient direction. So this g of s is actually our signal. So eta t attenuates not only the noise, but also the signal. So that means we want eta t to diminish to 0, but it cannot diminish too fast with time. If eta t diminishes too fast with time, then we will be attenuating the signal component, the gradient, too fast. If we are still far away from the optimal point, the gradient is still quite far from 0, but eta t is so small. We attenuate our signal, we will be moving so slowly, and we will incur a lot of regret in the process. So that's the difficulty with SGD, the stochastic gradient descent algorithms. How do we choose the step size? It cannot diminish too fast, it cannot diminish too slow. And what is the rate, the optimal rate this step size should diminish to 0 really depends on how the signal component, g of x, how the gradient of this unknown function is changing over time. So that's the function characteristics. Although the function we do not know, but SGD may require to know certain characteristics of the function in order to set the step size in an optimal way. So we can see here, essentially, the step size, eta t, is crucial to SGD. It manually controls the trade-off between learning rate, that's we want to preserve the signal component of our observation, and also we want to attenuate the noise so that we can really converge to X star rather than oscillating around X star. And how do we choose the optimal eta t depends on how fast the signal component is approaching 0 as we get closer to the minimizer X star. And that we need to know certain things about the function characteristics in order to know how the gradient is behaving. So let's take a look at the function characteristics. As we said, we're considering convex optimization. So we know our objective function is convex. What that means is at this, at any point, if we take the derivative, this is a tangent line, then the function must lie above the tangent line. So the function can be anywhere in this green shaded area. So that's just generic convexity. But we may be facing a better behaving function, the so-called alpha strongly convex. What that means is the function not only lies above the tangent line, it also lies within a certain quadratic function. This quadratic function would have a gradient of the curvature lower bounded by alpha. What this means is the function cannot be too flat. Okay? So it cannot be like very flat, very close to this tangent line. It has a lower bound on how fast the gradient is changing. So this alpha essentially gives us a lower bound on how fast the gradient function gx can change. Okay? So the curvature must be bigger than this curvature of the quadratic function that has essentially parameter alpha. On the other extreme is the so-called smoothness. So the quadratic function here, it lies above the tangent line, but also it lies outside of quadratic function. So this is called the beta smooth. What this means is the function, the GS cannot be changing too sharp. Okay, so we also want some smoothness. So the curvature actually is outside a very curved quadratic function with parameter beta. Okay, so this is so-called beta smooth. So beta essentially give a upper bound on how fast the gradient function GS could change. And the other extreme is actually non-differentiability at the optimal point X star. So you can see the optimal point X star, at the point there, the function is actually not differentiable. So we need to use subgradient. This actually make the learning problem easier in the sense that the signal, the gradient will never be 0. So the gradient actually change from negative to positive. It jump from negative value to positive value. It's not continuously changing from negative to positive when we approach X star. This actually makes learning much easier because the signal Gx never diminish to 0 when we approach X star. So these are essentially function characteristics. If we do know, although we don't know the precise function form fx, if we do know whether the function is alpha strong convex and also know a lower bound alpha, or the function is beta smooth and know an upper bound beta, or we know the function is non-differentiable and we also know what is the gap that the gradient jumps from negative to positive at x star, that information will be very helpful in setting the step size for SGD. And this would be the regret of SGD in different categories of the function characteristics. For example, if the function is convex and may not be smooth, this is a worse scenario. This is a very general class of functions. Then the regret will only be square root t log t. But if we know the function is alpha strong and convex, and we know alpha value, we can set our step size according to that. Then we achieve a much better regret, which will be log t squared. If it's non-differentiable, we know a bound on the gap in the jump of the gradient at x star, then we achieve the lowest regret, which is log t. And similarly, for beta smooth, we can choose the step size accordingly. Okay? So what the problem here is, in order to achieve all these corresponding regret orders, SGD needs to know which category the unknown objective function belongs to, and the corresponding parameters like the alpha value, the beta value, or the jump in the differentiability case. So then we can set the step size accordingly. And many empirical studies have shown that if we misestimate the category of the function, or we misestimate the parameter alpha or beta, then our step size may be way off, and the performance can be really bad. So it's sensitive to model mismatch, to estimation errors in the function parameters. So the question we want to ask here is it possible to have a learning algorithms that can self-adapt to the unknown function characteristics, which means the algorithm does not know ahead of time whether the function is alpha strongly convex or whether it's beta smooth or non-differentiable. The algorithm actually learns from the observation. And if the function is well behaved, like alpha strongly convex, then the algorithm will automatically give you a better regret order. But if the function behaves generically as a general convex function, then the algorithm will only give you a lower regret order that is achievable for a convex function. So that's what we want. We do not want to require the knowledge on which category the objective function fx actually belongs to, and have to know the parameter values alpha and beta. Can we have an algorithm that automatically learns that along the way and give you the corresponding regret order for the category that the unknown function actually belongs to? So that's the solution framework I want to present, and we will show we could actually achieve that, and also give regret order that is actually better than SGD in certain cases, or at least matching the regret order of SGD. And this is the basic structure of the solution framework, which we call random walk on the tree, as given in the title of the talk. So the first thing, I will focus on the one-dimensional case where the search space of the decision variable x is within a one-dimensional interval. Without loss of generality, I will set the interval to the unit interval from 0 to 1. So we're searching the optimal value, say here x star, within this interval of 0, 1. The first thing we do is we build a binary tree representation of the entire search space. Okay? So we do this through a successive binary splitting. So the root of the tree will just be the entire interval, 0 to 1, that's the entire search space. And then the next level, the two children, would be even splitting of the interval. So the left children is the left interval from 0 to half. The right children would be the right interval, subinterval from half to 1. And then you keep splitting. So this would give you, at the second level would be the intervals from 0 to quarter, quarter to half, half to 3/4, 3/4 to 1, and keep going. So we will be building a binary tree with infinite depth, because we can keep splitting. And the sum of the interval, recall every node on the tree will represent a subinterval. So some of the subintervals would include our optimal point x star. For example, the root, of course, include x star. That's the whole interval. And then this, the right node on first level would include x star, and then go to this one and keep going, right? So as we move down on the tree, we would be getting into smaller and smaller subintervals. And what we want is to devise a random walk on this tree so that we can keep zooming into smaller and smaller intervals of x star. That's how we approach x star. So that's the basic idea of this problem. You can view this as search first with very loose resolution. You take a big picture of the whole interval, and then you try to decide which part of the interval you want to zoom in that's more likely to contain x star, and you keep zooming in and getting closer and closer to x star. So we can see what we mean by a random walk. So let's just see if currently we're at this node, on the left node in the first level, which clearly we got there by a mistake because of noise, because this one doesn't even contain x star. So from this point, we will say the random walk is moving in the right direction if it essentially follows the shortest path on the tree to the x star. So essentially here we would have to go back to the root node and then go to the right children and then move down like this. This will be the right direction. And all we want is the random walk is biased toward the right direction, toward x star. We don't have to be very precise in our movement on the tree. All we require is it is more likely to move in the right direction rather than moving in the wrong direction. So the probability of walking in the right direction, as long as greater than half, then we are happy. The algorithm would work. So that's all we require. This is also one of the reasons there's no parameter we need to tune. The only thing is it will require the precision as long as it's more than half. Okay? In the right direction is more likely than walking in the wrong direction. That's the biasness we're talking about. So next, let's see how we move for this random walk. Let's just assume we are currently at this node. For a general example, we currently at this node. We need to decide where to go next. So there are three options we have. We can go back to the parent, or go to the left child, or go to the right child. Okay? Recall every node represents a subinterval of the search space, and for this node, it represents the interval from a quarter to half. Okay? So this is the interval. We're trying to decide whether this interval contains x star. If it contains x star, whether it's the left interval contains x star or right interval contains x star, so that we can decide whether we move to the left child or right child. Or if the interval is likely does not contain x star, then we have to move back to the parent and try to move to the other side of the tree. So let's see how we make that decision. How do we decide whether at this point we need to move back to the parent or to one of the children? So this is the interval we are currently in. That's from a quarter to a half. So what we're trying to do here is we're essentially trying to decide whether the gradient of the function has a sign change within this interval, because that's where x star is. If this interval contains x star, then the gradient will be changing from negative value to positive value. So that's what we're trying to decide. So what we'll do is we will first choose decision variable equal to a quarter. We try to test the left end point of this interval, that's a quarter. We try to see what is the sign of gradient at this point, a quarter. And we just want to decide that with sufficient accuracy so that our random walk has an accuracy of greater than half, if it's correctly biased. And so then After that, we will test what is the sign of the gradient at the midpoint, 3 over x. And then we test the sign of the gradient at the end, the right end point of half. And that will tell us whether there's a sign change here and where the sign change is. So let's see, this is the outcome of our test. So if we see the gradient at a quarter has negative sign, -1. The gradient at the midpoint has a positive sign, we use 1. And at a half, at the right point is 1. So then this tells us with required accuracy that there's a sign change in the left subinterval. So then the random walk should move to the left child, which would be going to this interval. We'll zoom into the left interval, left subinterval. But if the sign is this outcome, sign test, -1 to 1, so that means there's a sign change in the right interval, then we move to the right child. If it's any other combinations, then that means it's an inconsistent result. Then we might have come to this node by mistake due to noise, then we will move back to the parent. Okay? So that's how we do the random walk. Okay, this is the basic structure of the random walk on the tree that tells us how we actually move on the tree. The only thing left would be how do we decide the sign of the gradient at any given point. For example, let's take a quarter here. How do we decide the gradient at a quarter is negative, positive, with required confidence level, with required accuracy? And that's the last component in our solution framework. And this is given by a confidence bound guided local sequential test. Okay? So what we do here is we're trying to test the gradient, the sign of the gradient at a particular value x, as the example x equal to a quarter in the previous example. So what we will do is we keep drawing samples from x. We keep using the value of x to the system and see what is the gradient of the random loss at x. Assume we currently already have S samples. S here is the number of samples we have drawn so far at X. We can compute the sample mean, essentially it's the average of our observation in the past, and this is our sample mean. We compare this with a threshold, with a constant value. If the average is above this positive value, then we have reasonable confidence that the gradient is actually positive. And we will terminate and output 1. So we will see the sign is positive. On the other hand, if the average of the gradient value drops below a negative of this constant, the threshold, then we are reasonably confident the gradient is actually negative. We will terminate and output -1. Otherwise, if the gradient is somewhere in between these two thresholds, that means we're not yet confident enough, there's too much uncertainty, then we will take one more sample of x, so this s will increase by 1, then we will test again until we exit, until we terminate with either 1 or -1. So this is the local sequential test for testing the sign of the gradient at any given point x. Okay? So if we look at the threshold, this is essentially the so-called confidence bound. The sigma square here essentially is upper bound on the noise variance. So we need to know something about how big the noise is in order to decide how much we should trust our observations. And this Q here is our confidence level, how accurate you want your sign detection to be. And we just need this Q to be confident enough to make sure our random walk is biased toward X star. So essentially, the probability of walking in the right direction is greater than half. Okay, so it doesn't have to be very accurate. That will determine our essentially threshold for determining when to terminate. So this is the component of the random walk on the tree algorithms where we actually adapt to the unknown function characteristics. What that means is if the signal component, which is the gradient. If the signal component is strong, that means the gradient, the magnitude of the gradient is far from 0. We are still far from x star. The gradient still is far away from 0. Then our signal will be strong. In this case, we will be able to terminate quickly because we are seeing observations that's far away from 0. We will be able to either terminate with 1 or -1 quickly. We don't have to take too many samples. So we will be moving faster on the tree. But as we get closer to x star, the gradient will be diminishing to 0. So we're trying to detect something that's very close to 0, whether it's positive or negative. So we will be taking more samples in that case. So the algorithm is automatically adapting to the unknown signal strength, or how fast the gradient is changing to 0. That's where the adaptivity to the unknown function value is built in. And I also want to mention that when we are far away from x star, the algorithm moves faster so that we don't spend too much time at the suboptimal points, x star, that will make regret small. And when we get close to x star, the gradient is so small, the signal is diminishing to 0, and we will be spending a lot of time trying to figure out whether the gradient is positive or negative. But on the other hand, the regret is small as well because we are close to x star. So all those x we're trying is close to the optimal, our loss actually is small. So that's how we make sure the regret is growing at minimum order. Okay. So this would be the comparison of this random walk on the tree, we call it RWT, compared to SGD for different function categories. And we can see RWT offers better regret order than SGD in the general convex case or strongly convex case, and all the matching regret order for the non-differentiable case, which actually matches with the lower bound. But the key here is for SGD to achieve this regret order, SGD needs to know what is the category of the function, and also needs to know the parameters like alpha or the how much the function is non-differentiable. But for RWT, it does not need to know anything, right? So it automatically gives you a better regret order if the function is behaves nicer. Okay? So it matches or offer a better regret order without any prior knowledge on the unknown function. And it's robust. It has known tuning parameters to do. It adapts to the function characteristics. Any questions? I see I've already used quite a lot of time, and I would have to move a little bit faster for the second half of the second part of the talk, which indeed the main part we have already covered. That's the solution framework based on random walk on the tree. This is just mentioning we can also handle heavy-tailed noise where the variance is actually unbounded. There's infinite noise. Next question is, so far we only presented a solution for a one-dimensional problem. So the x actually lies in a one-dimensional interval. How do we deal with high-dimensional problems? Okay. For SGD, that's not a problem. You could just compute the full gradient and move according to the full gradient estimates. But the difficulty here is computing full gradient. There's a high cost, and also it's difficult to do parallel computation and also distributed computation. Essentially, if you have multiple cores that you can do the computation simultaneously. For SGD, it's difficult to exploit such parallel computation structures. So how do we actually extend to the high-dimensional problem? It's difficult to build a tree through binary splitting when we are dealing with a high-dimensional Euclidean space. So the idea here is actually borrow from what we already know in a deterministic optimization problem. So if we know the objective function fx, which is a deterministic function, and one way to solve a high-dimensional problem is to use a so-called coordinate minimization. That means each time we fix all the other coordinates and only minimize in one direction, in one coordinate of this function. And then once we find the minimizer in this coordinate while fixing other coordinates to the previous value, then we update this coordinate with the minimum value and then minimize along a different coordinate. We keep doing this until we approach the global minimizer x star. But this is when we know the function f. If we know the function f, we can find the minimizer in a particular coordinate quickly. Okay? But for stochastic optimization, we do not know this function. How do we find the minimizer along any given coordinate? Okay, so this is only saying all the advantages of doing coordinate minimization. First, it only requires a partial gradient. Each time we're only doing partial gradient computation along one coordinate. And you can do this in parallel across different computation cores. You can do distributed implementation. So these are all advantages. But the trouble is this is for a known function f. So how do we extend this to stochastic optimization, where we do not know f? How do we find the minimizer along a specific coordinate? Let's call it I of k. K here is each coordinate minimization iteration. So you can see, okay, easy. We can just view this as a one-dimensional stochastic optimization problem. So this is the decision variable is only a scalar in one coordinate, and f is unknown, but we can try to approach this minimizer in this coordinate ik using a low-dimensional stochastic optimization routine. Okay, the trouble here is when we try to approach this minimizer in this coordinate, all the routines would have to keep trying and try to approach it as time goes to infinite. So how do we know when to stop? Okay, we cannot be moving in this direction forever because all the other coordinates may be far away from the global optimum. We don't want to keep minimizing along this direction because this direction may be far from the global optimum. So that's the key question. To what precision we need to minimize in a particular coordinate while fixing other coordinate values? So that would be the key question. And let me just wrap up that with a quick overview of the solution we have here. So the problem essentially we try to extend any low-dimensional optimization routines to solve a high-dimensional stochastic optimization problem. So we can essentially formulate the problem in two steps. First, we need to decide in each coordinate minimization iteration k, how precise we want this minimization, one-dimensional minimization to be. So how close we want to get to fx star at each coordinate. So that's the precision control epsilon k. We want to get to epsilon k close to fx star. And at the beginning, you can imagine, because all the other coordinates are far away from the optimal value, we do not need to require to be very precise. We won't be able to do it anyway. So we can see this epsilon k should be diminishing as our iteration goes, the so-called progressive coordinate minimization. And then we also need to design a termination rule for the algorithm. The algorithm needs to know when to terminate for a given precision. Okay? Because the algorithm doesn't know the optimal value of the function. So it may not know exactly how close it is. So we need to have a stopping time or termination rule for stopping at the required precision. So these essentially are the two questions we need to answer. And our objective is we want to achieve the same regret order as we do for a low-dimensional problem. So when we're facing a more difficult problem, a high-dimensional problem, we want to preserve the same efficiency as the algorithm has for low-dimensional problem. And I'll just summarize with these slides. What we have shown is the optimal precision control is essentially a geometric sequence with the coordinate minimization index k. And gamma here is a constant that needs to be, is smaller than 1 constant so that the precision we're getting closer and closer distances to the optimal value dimension to 0. And the striking thing here is this optimal control is independent of the low dimensional routine you are using. For example, we could be using the random walk on the tree, or you can use a low dimensional SGD, any other low dimensional algorithm. It doesn't matter. The optimal control of the precision actually is the same. And it's very, essentially very general. It applies to all noise distributions, including habitat distribution, and it's efficient for parallel and distributed computation. And this actually is optimal if the function is strongly convex and separably non-smooth. We're currently trying to extend this to a general convex function. So I will just stop here. Sorry, I have used more time than I supposed to. So next, I'll be happy to pick questions. And these results are already published. If you're interested, you can check out my website.
Thank you, ma'am. You can carry on if you want. Like, if you can wrap up in like 5 to 10 minutes, you can carry on. Currently, we don't have any questions from the attendees. Attendees are requested to pose their questions in the chat box, or you can also unmute yourself and ask directly. Okay. I don't think we have any questions. Ma'am, you can either carry on or wrap up here. It's on you.
For me, yeah, if there's no questions, I guess we can wrap up here. Feel free to email me if there are any questions come up after the talk.
Sure, ma'am. Okay. So this is it. A big thank you to Professor Zhao for her efforts in directing us towards this talk. And we hope that it will be useful in research or work for the audience, and all the students should be benefited for this talk. I thank you from the bottom of our hearts to Professor Zhao for accepting our request and conducting this talk so swiftly. Thank you so much, ma'am, and thank you all the attendees
for organizing. Oh, I see a question.
Yeah.
Can this approach be extended to momentum-based methods? I'm not very clear what you mean by momentum-based. Are you talking about the adaptive SGD type of algorithms where the step size adapts to the to potentially higher orders of the gradient observations? Yeah, I assume, I don't exactly know NAG. I assume you are talking about certain accelerated version of SGD. So RWT in certain way goes, it's a very different design principle from gradient descent, because it will not moving directly in the gradient direction, right? So the movement of the random walk on the tree is actually structured. So we're not moving in any potential direction along the gradient, which can be anywhere. It's a continuum movement. Any points in the continuum space might be hit by the algorithms. But for SGD, we will only visit a discrete point, which would be the end point and the midpoint of all the subintervals. So it's a very different algorithms. So how the RWT compare with accelerated version of gradient descent? So many accelerated version of gradient descent often require, for example, second order knowledge of the gradient. They may have to compute the hashing of the function. So there are certain issues there. And again, those type of functions require those type of algorithms require certain knowledge on the function statistics in step size. So there's again an issue with the step size. So in certain way, RWT give you a structured movement, random walk, in the search space. In gradient descent is unstructured. You can, depends on the random noisy observation of the gradient, which can be anywhere because of the noise. You may be moving anywhere in the whole continuum search space. But for the random walk on the tree is a controlled mobility. We will only be hitting specific points. Essentially is all the binary expansion, right, of the X star is like a quarter, half, and all the midpoints. So that's where, in certain way, we do not have to control the step size, and the adaptivity is built in the local sequential test. Yes, the next question. I'm actually not very sure this orthogonal matching pursuit. I'm not aware of other works that essentially builds on this random walk structure on a tree representation of the search space. I'll be happy to check it out and see what the differences would be. Okay, thank you for the question.
Yeah, do we have any more questions from other attendees? Okay, I think we don't have any questions. Thank you, ma'am. Thank you once again for your time. And
thank you.
Yeah.
It's nice meeting all of you, and
it's nice to meet you, ma'am.
Bye for now.
It's nice to meet you too. Have a nice day.
You too. Bye.
Thank you. Thank you all.